And that puts us to Ed Gernert from Frontier Design. Some of you may have seen Ed's presentation he did previously.
So Frontier Design was launched in 2019, specializing in shape-based autorouting. We currently have a patent pending high-performance, high-capacity shape-based architecture. We support standard cell, chip assembly, and any mixed type layouts. Our goal was ease of use. We're fully GUI driven and no complex setup at all for the router. You basically read in design, set your constraints, and hit the auto route button. We support both Windows and Linux, and we wouldn't be here except for OA. So thank you, OA. One of the challenges we started working on a couple months ago was threading. And we picked OpenMP, which stands for Open Multiprocessing. OpenMP has been around for a while, first released in '97. It's an API that supports shared memory multiprocessing on C, C++, and Fortran. And OpenMP supports two flavors, MPI, which is basically a cluster of computers connected together, or within a single node using internal cores, and that's what we're supporting right now. It consists only of compiler directives that influence threading. During compile time, it converts the preprocessed directives into native C++ code. The pros of OpenMP is really there's no dramatic changes in the code needed. The cons are it's difficult to debug synchronization and race conditions, and you have to be very conscious of what's happening at all times. A simple example that's just going to print out the loop count and the thread number. And for OpenMP, all you would need to do is add in this directive, pragma omp parallel. It says the next statement must be a loop. And basically, it's going to take the main thread, and it's going to spawn different threads out for each pass of the loop until it's done processing. And then the threads are killed, and then the main thread continues again. So the output's going to be loop count 1, thread 1. It doesn't go in order, so any thread it wants can start next. So thread 3 starts, thread 4, thread 2, back to thread 3, 1, and so on. So it's very simple to create something that's multi-threaded using OpenMP. OpenMP only has about 30, 40 directives that you can actually specify. You can specify how many threads should be used, what's a critical section, which means only one thread can execute this at a time. All the other threads must wait. You can find a parallel region. We discussed a barrier that says all the threads must wait here until they're all finished, and then you can continue. So you can have nested parallel threads that start up. And you can say only the master thread can execute this code. Those are the 5 top ones that we use. As I said, OpenMP shares memory. So all threads have access to the same data. One of the downfalls is threads can't simultaneously read and write to the same memory location. Crashes, you're going to have unknown data states, really bad things can happen. So you have to be very conscious of what you're doing and when you're doing it. OpenMP provides a locking mechanism, so you can set a lock, unset a lock on an object. If an object is locked, all the threads will wait in the idle state until that object is unlocked. And currently within Frontier, we developed an object protection scheme within our patented database that we can lock by any object, by a shape, by a pin-to-pin connection, or by a net. So an example is on the right-hand side, I have 3 nets, red, A, B, blue, C, green. So if net A is routing, it's locking the area that it's routing in. Now, if net B starts and net C starts, it's going to wait for A to finish. Once A is finished, the next net that's waiting will take over that area, and now B will route, and now C will wait again. In this small example, threading doesn't buy you anything. Actually, it probably hurts you a bit because there's a little overhead for threading. So due to race conditions locking, performance is not linear. 4 threads does not equal 4x performance. Autorouters are very unique that they create data. They're not checking data. So it's very hard to parallelize a router. Here's an example of 2 million connections. And you can kind of give an understanding of the complexity for threading something like this, because everything's crossing it at the same time. And that's our head right there exploding. So lessons learned. We spent more time writing self-debug code than the actual OpenMP threading. They're adding directives. With threading, everything happens in parallel and extremely fast. So 16 cores means 16 things can happen simultaneously, and it's hard to step through code one line at a time. OpenMP is not forgiving on locks. You can't lock the same object twice, or it'll crash, or you can't lock, whoever locks an object must be the thread that unlocks it, and need to protect all data that can get written and potentially read at the same time. It's going to end up to collisions, crashes, bad data, unknown data down the road. That's why we spent a lot of time writing the self-checking. Within some threaded functions, some code snippets must be executed serially, like a counter, for instance. You wouldn't want to go 1, 2, 3, or 1, 2, 1, 2, 3. So you got to protect on that. As part of our initiative of ease of use, we show the graphics at all times. And graphics was one of the challenging parts of OpenMP. Within Frontier, you can pause at any function and display any shape object. Now we have to stop, pause all the threads, regardless of what they're doing, and then to show that one object. There are some decent tools available for debugging. Visual Studio is pretty good. There's an Intel VTune profiler that's pretty good, and Total View on Linux is very good. Here's an example of a 450,000 connection standard cell. And what I want to point out before I run the video is on the top, here's two threads. Thread number 2 contained an area that's encircled in the yellow, and it's routing that thread. And now 15 also wants that area. And so what we do is we highlight a diamond shaped as soon as we find that that portion is locked. So you'll see these diamond shapes pop up. Thank you, Marshall. Okay, so the router is routing. Oh, it is very blurry. So there's actually some thread numbers within the boxes. And I guess the important thing to see is the white diamonds. That's where an area is locked. On the bottom right, it shows you the CPU usage. 100% is on top, so we're doing about 30–40% of CPU utilization right now. All the other ones are locked. So we're sampling this design probably every 50 connections or something to do our debug display. And the graphics so fuzzy is just the graphics. It's the capture of that. So you can see on the left-hand side, this is real-time autorouting for 450,000 connections. It's putting in all the connections. And the top right is just showing a reflection of what the locks are doing. And right now, as it's progressing, we're about 50% utilization. Again, this is real-time on a 450,000 connection design. And as the router progresses, it's doing the long connections first, and then it'll start working on the shorter connections, so it'll actually get faster. So now we're about 70–80% utilization. And I think in the bottom middle, there's a number that displays it's moving. I don't know, it's 40% done or something. Oh, on the left-hand side there. That's okay, Marshall. So now you can see it's about 60–70%, and it's faster, faster, faster. Utilization is 100% CPU. So we are maxed out. So all the CPUs are running at the same time. So we're done now at this point. So it's routed 450,000 connections with 16 threads on 8 metal layers, and it took 2 minutes. So the yellow arrow shows you the design that we just routed. It took 2 minutes and 1 second on 16 threads. And if I run it on one thread, it's at 5 minutes and 49 seconds. So this shows a table of different designs. There's a design with 108,000 up to almost 4 million connections. The 4 million connections I ran on a different machine with 24 threads. It has 256 gigabytes. For 4 million connections, we routed in 3 hours, 52 minutes with threading versus 11 hours and 23 minutes without threading. And then you can really see if you look at 16 versus 8, there's not much change. When you go 8 to 4, there's a pretty decent change, down to 2 threads, down to 1. So it really doesn't buy you that much by maxing out your threads. But if you can do 12 or 8 threads, it really benefits the router. But the point of this whole exercise was to show that we can speed up the router. The router is very fast natively, but we can still speed it up with threading. I want to say one thing is we executed Quick Route, which is one of our internal routers. And every design that's here routed and achieved greater than 99.5% completion with no conflicts. On the 450,000 connections, we had 1,200 unroutes. I haven't finished the detail part routing for the threading, but when I kicked off the detail router, it took 15 minutes to close all those 1,200 connections. So total route time from 450,000 to zero conflicts was under 20 minutes total. So what's next for us? Performance with threading can still be improved. We're going to minimize weighting of the threads by clustering of localized connections. So the picture on the right, net A, B, and C, those don't need to be threaded because ultimately one of them or two of them are going to be waiting for the next thread. So we can run them on the same thread. So A completes and B starts and then C starts on thread 1. In the meantime, thread 2 can do D, E, and F, and there's no waiting. The same with thread 3, can do G and H. So that's the next level that we're going to be working on. We're going to enable the remaining functions for threading. Global Assist, which is our version of the global router, adds another level of complexity because you don't really know what the area that you're going to route in. So if you're routing net A and there's a big blockage in between there, you're going to have to go all the way up, possibly to the top of the chip and then back down again. So we know how to fix it. We'll just add another level of complexity. Functions that just read the data, not write, can all run in parallel. Things like checkers, the graphics, etc. So those can just be parallelized. You don't need to lock anything. And we're going to run some larger test cases. The database we know can support much larger data. We haven't figured out what the top end of our data limit is yet. So what's next for us? The never-ending constraints, advanced nodes, advanced features. We're still hiring. We have 3 engineers right today. And this is something I want to stress to everyone out there. We're looking for customers, beta customers, to help us. If you know of anybody who can use an Autorouter, please send them my way. The benefits, do you need more features from your current Autorouter? You want faster turnaround time? The next technology, you want to influence the next router? You get personalized support and you'll have free access to a license for the router. So we're really looking for customers. So if anybody can help, I would really appreciate that. As a small company, it's hard for us to get some of the constraints, but we want to understand what the constraint is and how we can support that within the router. maybe just a global version of it, not the actual details, but we do need help. And I want to thank SI2 for once again allowing us to present and showcase our product. We do have a website that has some demos on there. It's fairly old, but it shows you what we can do. This is just more information. Someone asked about what the constraints we currently support. These are the constraints that we support. One of the things that we're working on next is coloring. So it was interesting to hear about what OA supports for coloring.
Hey, Ed, these constraints, do you get them directly from OA?
Yes. We'll also provide another means at some point. So if the constraint's not supported in OA, it'll be some file that we read, which is no deal, big deal. But today we read all the constraints from OA, yes.
What was the crude process node that you guys used for your example here, Ed? Was it 65 nanometer class?
That was probably 65, yes.
Okay.
Yeah, so we support somewhere around 65 right now, give or take a little bit.
Quick question, Ed. You mentioned the name OpenMP. Are there any, is there any possibility or plans to contribute that as, say, for example, an open access extension, at least the basis for multi-threading? That might be interesting.
Well, OpenMP is existing for the last 20-something years. The compilers support it. So if your compiler supports OpenMP, then you have OpenMP. So Visual Studio supports OpenMP. We're compiling on Linux on Red Hat. That supports OpenMP. So it goes back to the compiler. And since you're adding compiler directives, if your compiler does not support OpenMP, it's a no-op, basically. It just skips over it. So your code runs just originally, but there's, again, no threading. So we have no control over the OpenMP. We're just using that to do the OpenMP, to do the threading. It alleviates us creating the threads, joining the threads. It saves us a lot of work.
Yeah, let me reformulate my question. Sorry. It was more along the lines of specifically working with open access. I think you mentioned that there was quite a bit of code that had been developed to debug things and so forth, and maybe work with open access in particular. It was more along those lines. Okay,
so for open access, we read open access and we write open access. So we write the OA routes going back into open access. Okay. Yeah, I don't see where anything that we can support. Maybe some of the translator stuff. I know there's translator development that's going on in open access. We might want to contribute some of that stuff. So since we did all the work to read the constraints, read the layout out of open access into our format. So we have our own database. So we don't run on top of open access. We have our own format very, very fast.
Okay, that helps answer. Thank you.
Yes.
But are you doing at least multi-threaded reading of the open access database?
No.
No. We don't. Tried?
No, because that's just partitioning, right? Threading for open access. So we would read the whole design in, congest the whole design in, and then we need to partition it because we don't know what's crossed the boundaries. So within partitioning, it doesn't help us for open access for threading because we don't know what connections are routed across other connections, right? Mm-hmm. In open access, I can pull out an area of open access to route, which is fine, but that doesn't give us the bigger picture of routing everything at one time.
Right.
Maybe a silly question because I come from the photonics domain, don't have a lot of electronics knowledge, but these routes, since it's parallelized, are they deterministic? Like if you would run the same thing twice, would it give the same routes? Or is that not a requirement in electronics?
It would not give the same results because you don't know the threads are, they're not the same, right? It's whatever the OpenMP decides at that point that thread is available to throw at it. If you want something that's going to be deterministic, you need to run it non-threaded. And that hasn't been an issue so far with us. We haven't needed that. I mean, the router itself is very fast. So on that 450,000 connections, instead of 2 minutes, if you're running it non-threaded, it's, I don't know, 11 minutes or something, whatever, 6 minutes, 7 minutes. It just adds another, bullet in our chamber that says, our router can support faster and faster and faster.
I've got a question. Also maybe a dumb one because I'm an analog guy. When your router finds that it requests like blocks to route in and they're unavailable, it just waits until they're available, right?
Yes, correct.
Is that efficient? I mean, couldn't it just take that route and throw it back in the to-do pile and grab another one?
It could. There is actually something in OpenMP that says don't wait on your thread, but skip it for right now. But then you're really going to be skipping a lot of nets. There's a lot of overhead with that. So if you go back, Marshall, to the slide where it has what's next. So we have all of this code done, the clusters, the connections. I just haven't finished it yet. So in this case, thread 1 is going to work on A, B, and C. So it will do these serially. It'll do A, and nothing's waiting at that point until A is done. So it'll do B, and then it'll do C. So we will get a huge bump in performance when we go to this model of the clustering. So today it's throw everything out there and just let the router sort its way out. And we're getting a 4x improvement. This is going to add another much bigger bonus onto the threading when we implement this or get this running. It's all implemented. I just haven't got it fully debugged yet.
Okay, so
and then there'll be no waiting in this case, or
right.
Very little waiting.
So I'm just interested in how it works. So with this MP threading thing, do you have, if you decide that you've only got 8 cores, does your software manage the fact that there's only 8 cores, or can you create 20,000 threads, but MP thread knows to only activate 8 at a time because there's only 8 cores?
Oh, you can tell it what you want. So in our case, we have a GUI, and the GUI has an option of 1, 2, 3, up to the maximum cores. If you specify 100 cores and OpenMP only finds 4 cores, it's only going to run 4. So OpenMP has the final say, and we also have a way to control that.
In your 400K example, was this just routing or also strategies like rip up and retry?
This is just routing, and the 15 minutes that I said to finish the 1,200 connections is the rip up and retry.
Okay, so it will also rip up essentially existing routes to get the missing 1,200 in.
Absolutely, yes.
Okay, and how much is that parallelized?
I'm sorry, what was that question?
How much is that running on OpenMP in parallel on multiple threads?
Right now it's not. I haven't implemented that function yet.
Okay.
So the second bullet here, enable the remaining functions. So the 15 minutes to finish up the 1,200 connections, that just ran on 1 thread.
Okay.
So in the near future, I'll enable the rip up and reroute and everything else to use threading. So that 15 minutes will go down to some other number that's much smaller.
Right. In the beginning, you said you are starting with the long nets.
Yes.
Isn't that kind of counterproductive instead of starting with the small ones?
No, absolutely not.
Did you run experiments on how the behavior would be running it vice versa?
Absolutely. Even without threading, you really want to do a shape-based router long to short, because you want to put the long ones in as straight as possible, right? If you do it the opposite way, you're going to have all these little tiny segments all over, and then you're going to get to the last long connections and start putting them in, and it's going to jump up and down and add, thousands of vias.
Oh, that's a good point. Yeah.
Yeah. So that's basic routing 101. Something we've learned from, just building routers. You always want to start long nets to short nets. We have an option in our router if you want to try short nets, long nets. There's probably 15 different options you can set within the router, and that's one of them.
I have a question. Are you planning to add a placement tool to your product? Because usually when you buy these things, it's a place and route tool, right?
No. Yes, we're not doing placement. We are specifically focusing on routing.
Are there companies that sell purely placement engines?
That I don't know about. They probably bundle place and route. But we would interface within some tool. So let's say you have a Cadence or a Synopsys tool or a Magma tool, not Magma, Siemens tool. You can use our router versus their router. Again, we support open access. So you would do your placement, you do everything else, and when you want to do the router, you would come to our tool, route it, send it back through OA, and then back into their tool.
Right. Okay.
We are just focusing, and that's where all our expertise comes into routing.
Mm-hmm. Okay.
Hi, Ed, Ali here. You said with the introduction of this parallelism, you had to do a lot of self-checking, spend a lot of time on self-checking.
Yes.
What does that mean?
Well, self-checking in terms of you don't want to write over some data object when you're writing a data object and then you're reading a data object at the same time. That's going to cause you problems. Maybe right away, maybe 10 minutes later. So there's a lot of checking in our code that says, okay, if you're threaded and you're writing something, are we actually trying to read that data at the same time? And if we are, then let me flag that. And oh, now I got to go fix that part of it.
So,
so there was a lot of checking that we did for the locking mechanism. The graphics that I showed you running with the yellow, the red and the white diamonds, that just gave us a feel good that, okay, we know that the threading is actually working. You can see the threads pop in and out.
all right.
You know, if you kick off a router and it goes into a black hole, what is that? Is that really telling you that it's really doing something? Or is it doing too much, too little? So we spent a lot of time in the self-checking.
I see. So this is mostly just to make sure that the locking is, the timing of locking and unlocking of objects is done correctly.
Yes.
Okay.
And then the graphics took a lot of time. Because you're doing well, on my machine, I have 16 threads, so 16 cores. So, you know, you're doing 16 things at one time, but you're showing the graphics still. So one of the things we do is we hijack one of the threads. So actually we're really using 15 threads for routing and one thread for the GUI. So the one thread is just doing GUI operations. And then the other 15 are really doing all the work behind the scenes. And we just queue up all the graphics and then display the graphics when it's available, threads available, the GUI threads available.
All right. One other thing that you mentioned was that one of the cons of OpenMP was the I think you mentioned it is basically the managing of the locking, unlocking, and things like that. Do I recall that correctly?
Yes, it was on the first slide, I think, or the second slide.
Right. So
it's the locking and the race conditions.
Race conditions and things that are common to multi-threading. So OpenMP doesn't have any magic in that regard. It's basically handles the thread pool automatically for you. Basically, it gives you an option of not to have to deal with all the details of which thread is doing what. But when it comes to other issues and challenges of multi-threading, you got to be careful as you're using threads or p threads and such.
Absolutely, you can easily shoot yourself in the foot with OpenMP.
Mm-hmm.
And that's why most of the time was on debug, so that we can catch things as they happen. So if we find out that let's say thread 1 locked an object, and then thread 2 is going to try relocking that object, we'll catch that. Because what happens in OpenM3, it just crashes. So it crashes and it just goes down. The whole system goes down, you're like, well, why? It's not very forgiving.
All right. Thank you.
But I highly recommend OpenMP. It's a great tool.
Yeah, one of the beauties of it is basically portable, as
Yes.
opposed to pthreads and things like that. Yeah.
Yeah, as long as the compiler supports it, which most do, and it's been around for 25 years, OpenMP. Any more questions? All right, find me a beta customer, please. Thank you.